Good morning, everyone. My name is Jackie Kenyak. I'm the Program Delivery Manager in Asset Management for BC Nonprofit Housing Association. And I'm pleased to be moderating today's webinar, Building Overheating and Air Quality Considerations in New Construction. This webinar is being delivered from various locations on the unceded traditional territories of the Coast Salish people, home of the Musqueam, Squamish, and Tsleil-Waututh nations. We acknowledge that many of you are currently located in the ancestral lands of Indigenous peoples across the province, each with their own unique traditions and history. At this point, if you have any technical questions or issues, please type them in the chat box, or you can contact info@Bricks Studio. That's Bricks with an X, bricksstudio.com, or by phone at 604-681-0295. This webinar comes to you today as part of a series in partnership with BC Nonprofit Housing Association, the City of Vancouver, and BC Housing. And last year we presented on the health impacts of extreme heat, and we're joined by doctors from the BC Centre for Disease Control. And a recording of that webinar is available on our website. And we have 2 more webinars coming up in May, both pertaining to extreme heat and poor indoor air quality in existing buildings. Today's webinar is all about new construction, for which I'll provide a brief outline of the format and introduce our speakers. The presentation portion of the webinar will take approximately 70 minutes, after which time the presenters will address questions, for which we've allotted around 20 minutes. Our goal is to finish up by 10:30 or sooner. At any time, please feel free to type in your questions using the chat feature, and then we'll do our best to address all questions during the Q&A segment. And this webinar is being recorded and will be sent out within a few days. You'll be able to access the PowerPoint via the recording, so you don't have to worry if you've missed something today. And at the end of the session, we'll send out a quick evaluation survey, and we'd appreciate you taking a moment to complete it. And I'd like to introduce today's speakers. First, we have Lisa Westerhoff. She leads the Sustainability Policy and Planning team at Integral Group in Vancouver, where she works with local governments, universities, developers, and industry organizations to create policies and strategies for a low carbon built environment. Lisa holds a PhD in urban sustainability from UBC and is the author of several academic publications on strategies for increasing climate change resilience and energy and emissions reductions. Lisa also holds a master's degree in climate change resilience and adaptation, and was the winner of Canada Green Building Council's Green Building Champion Award in 2019. Next is Sadia Afrin. Sadia has over 10 years of working experience with BC Housing and a variety of social housing construction projects. She has an academic background in civil engineering and business administration, has led a wide range of projects and initiatives, and continually makes improvements in BC housing design and construction. Her work involves creating a series of guidelines and standards, including design guidelines and construction standards, shelter design guidelines, modular design, commissioning, and women's transition and supportive housing guidelines. And Chris Dole is from Integral Group, has nearly 18 years of mechanical engineering experience, delivering cost-effective and sustainable mechanical engineering solutions for clients across many sectors. He draws on extensive industry experience within the Canadian construction market and further afield in Europe. Chris is well-versed in all aspects of sustainable building design, focused on high-performance buildings, and more recently, resilient building design. Finally, I'd like to acknowledge our graphic recorder today, Lisa Edwards, who's participating in the webinar. Lisa is a consultant for getthepicture.ca and will be creating a visual recording of the webinar, which will be sent out to all participants. We're excited to have Lisa join and look forward to the visual summary with key points from our discussion. And without further ado, I will pass the presentation over to Lisa Westerhoff.
Great, thanks Jackie. Very happy to be here. Thanks for having us and excited to present to you guys today. on resilient housing for a future climate. So I'm going to be spending about 20 minutes talking to you about different dimensions of the climate change challenge from the perspective of resilience and adaptation. This is just a quick overview of the presentation that I'll be giving you today. So I'll do a little bit of a background on why we need to care about designing for a changing climate. What are some of the data and trends that we are aware of that are coming out currently? I'll look at what the implications for housing in BC are a little bit more specifically, and I'm going to introduce you to some concepts around resilient building design. What does it mean to be a resilient building? And just give you a quick teaser on some of the resources that have been developed by BC Housing already. Hopefully you're aware of them already, but if you're not, then we'll give you a little quick tour. And then I'll pass it on to Sadia and Chris, who will get more into like the nitty gritty, the design details of how we can actually improve resilience in the building sector. So I'll start here with a little bit of a background on why we need to design for a future climate, or rather more, what is the current state of play with respect to designing buildings in general and housing more specifically. And what's really become obvious in the last little while is that we are increasingly drawing on data that is no longer relevant for our current and our future buildings. Historically, we use past data, climate parameters like temperature or humidity to inform how we design our buildings today. And if you look at the gray line on this graph, you can kind of see like there's this sort of natural fluctuation in temperature, average temperature across British Columbia. And what we do is basically use an average of that to inform the BC building code and to say, okay, this is sort of the average that we need to design our buildings to. But if you start to look at the colored lines on that graph, we're actually, with the global climate change projections and the data that we've collected, we know that historical data is not going to be relevant for much longer. So these colored lines on the graph indicate kind of a best, worst, and a moderate case scenario for what our future climate will look like. This is actually just an average temperature increase for the province of British Columbia. And you can see that while in the short term, those trends are kind of aligned up until about 2040, 2050, they start to branch or diverge quite significantly when you get to about 2040 and onwards. So what we need to do is try to figure out, what is the future that we're designing for, and how is that going to be different from today? What are the kind of parameters that we should be considering, and what are the thresholds that are different to make sure that our buildings today are going to be resilient or, well suited for the climate for tomorrow? And so while there is a bit of uncertainty as to which direction we're going, we do know that, in order to take the precautionary principle and design for the worst case scenario, a lot of recommendations are saying, let's use that top line as a guide for where we should be aiming in the future. And that way we know at least we're considering all potential futures. And actually, we already know that some of the climate has already changed. This is some data that's been released by the province of British Columbia that just shows that over the last century or so, we've already seen some changes in our climate across the province. So with respect to average annual temperatures, you can see that in some regions of British Columbia, we've already seen an increase from somewhere, in the area of 0.5 degree to upwards of 2 degrees or more over that last century, and we expect that trend to continue. If you look at precipitation, there's also some changes that have occurred there. We can see an overall increase in our precipitation, but with a lot of that rainfall happening in either the shoulder seasons or in the winter months, as we see in most regions or many regions that actually summers are becoming not only hotter but drier as well. So lots of things that are already being recorded. If we look at the future, this is downscaled to the Metro Vancouver area. But if we look at that, if we use that kind of worst case scenario projection, what the Pacific Climate Impacts Consortium, or PCIC, has found is that when we downscale those climate projections to a more regional or more local level, we can start to understand what that actually means in a more granular sense. Excuse me. So for the figure on the left shows the sort of the average number of days above 25 degrees Celsius for the period, that historical period of around 1970 to 2000. If you look at the graph on the right, this actually shows the same, the projections for how many days above 25 degrees Celsius that we can expect in the 2050s. And you can see it's over a doubling in the number of days above that 25 degrees. So basically, what does this mean in a nutshell? Overall, we're going to have warmer temperatures in the summer for this region. We can also look at estimates for increases in the number of very hot days. So there's extremely warm days, extreme events. And in this case, that's considered any day with a temperature threshold above 30 degrees Celsius. And same thing, you can actually see that in the historical period, there have been very few days over 30 degrees in the Metro Vancouver area, but that increases about sixfold in terms of an estimate for the 2050s. So not only higher temperatures overall, but also higher peaks and a greater number of peaks of those very high temperatures. I know for Vancouver, some of those estimates are in the areas of 35, 37 degrees Celsius. So quite warm, especially for this part of the world. So what does this mean for not just Metro Vancouver, but across British Columbia? Well, we know in Vancouver Island, we're expecting similar projections to the lower mainland, so that doubling of days over 25 degrees or more, with an increase in the number of extremely hot days as well. For the interior and the Cariboo region, we can expect hotter and drier summers overall, with a longer dry season and an increased risk of wildfire. And I'll talk a little bit about what the implications are for air quality and on that point in a moment. And then in the north, we know we're expecting a little bit actually wetter summers, but also warmer summers as well. So you can see that the variation is quite different region by region. And PCIC, Pacific Climate Impacts Consortium, has the ability to downscale kind of global climate projections for different regions so that we can understand more specifically what that means for each region. What does that all mean for the building sector? Well, we know that really this has implications for the way that we are, can occupy our buildings comfortably and safely. As I said at the beginning, this really just means that buildings that are designed for today's climate are not necessarily going to be suitable for tomorrow's climate. In fact, they're not likely to be. And that's going to need to require us to think about some additional measures for how we can ensure the comfort and safety of occupants in the future. So we can think about that in terms of thermal comfort. So am I able to occupy my suite or my office comfortably in the way that I want to? Can I use it in the way that it was intended? Can I sleep there at night? Can I work there during the day, etc. But it also starts to think, we have to start thinking about not just comfort, but also safety. So that's when we start to think about risk of overheating. So you're no longer just uncomfortable, you're actually at risk of increased morbidity or disease or heat stress, heat stroke, and a number of other kind of diseases or illnesses that can be exacerbated by extreme exposure to extreme heat, excuse me. And the sources of overheating, well, or the factors that contribute to overheating, I mean, there are a number of those. Not just outdoor temperature increases are the only factors that are at play here. And I know that Crystal will speak a little bit to some of the ways that we can mitigate these sources of overheating. But, in general, we need to start looking at how an increase in overall temperature or those extreme heat events start to interact with other factors that contribute to overheating. So one good example is that we will have, with increased temperatures, you may start to get hotter in your unit. You want to open your window. But if you're in an area of high traffic, if there's noise outside, or if there's a wildfire, an air quality event outside, you may want to keep your window closed, in which case you won't have access to that natural ventilation that you normally would. There's also appliances or activities that go on inside the home that can influence, how much overheating a unit or a building takes on as well. So it's really just about thinking about not only how the external temperatures are changing, but also how these other factors work together. Speaking of wildfire and air quality advisory events, that is also a trend that we need to be aware of as we consider overheating and the risk of overheating in buildings. And the reason for that being is that while we already know that we're already seeing an increase in some of these wildfire events across the province. And these are already having implications for the buildings that are directly in the path of these events. But they're also, not only do they have implications for buildings directly in their path, but they also have implications for those that are around the province that are affected by wildfire smoke and air quality advisories. So these are already occurring, and they're expected, just like increasing temperatures, they're projected to increase in their frequency and their magnitude in the future. And also just to keep aware of is that these are of course not, discrete events on their own that need to be taken into consideration, just like overheating, compounding with existing other sources of heat in and around the unit. So too does wildfire smoke compound with other sources of air pollutants that may be around a building. So things like traffic outside or industrial activities. And increasingly, the pollen that we're seeing, I don't know if you guys have had the same experience, but my allergies have been terrible this year. Those kinds of sort of high pollen concentrations are expected to only increase in the future as the growing season extends. So need to think again about how those things all fit together. And most importantly, so for the purposes of this workshop or this webinar, I wanted to think really about, how these hazards kind of interact to create impacts for not just the housing sector, but for low-income housing specifically. And the reason why this is so important is that while these kinds of hazards have impacts to everyone will be affected by them to some extent. We know that low-income households already bear a disproportionate burden when it comes to morbidity and disease. And that's as a result of a number of factors. They're often, not always, but often have higher exposure to things like extreme heat events or air quality advisories, possibly because of where their building is located. It may be in a downtown core area where there's an increased risk of the urban heat island effect, sort of that overall higher temperature in the urban environment. We know that they can be more sensitive to exposure or to these hazards. There's a lot, elderly populations, people with pre-existing medical conditions, they're already going to be more sensitive to an increase in temperature or air quality. And often they have fewer resources to draw on in order to cope or manage with something like this. If they're feeling sick, they may not have the ability to take time off work or seek out the medical resources that they need or the support that they might require in order to get through something like this. So again, everyone is touched by this, but we want to be particularly attentive to how these kinds of hazards will impact upon priority populations. So all this to say that, we are currently thinking about designing and operating our buildings as though it's kind of business as usual, and we're drawing off the data and the thresholds of the past. But we know what we actually need to do is to increase, is to change our thinking about how we design so that we are designing not only for comfortable, safe, and resilient buildings today, but also those that will be able to remain comfortable and safe for the future. So we need to think about how the design parameters for our buildings need to shift to accommodate, the worst case scenario ideally, but also just to accommodate uncertainty in general, which is obviously, a significant challenge for designers as they have to think about what is a cost-effective way to construct and manage a building today that will also be, resilient or adaptable to the future. So that's where we start to think about adaptation and resilience in the building sector a little bit more specifically. So I've used the term, resilient or adaptable a couple of times, but what I mean when I say that is really, or when we think about resilience or adaptation, what we mean is the ability of an organization, a person, a household, a building, any kind of entity to anticipate, to prepare for, and to respond to any kind of hazardous event. So something like an extreme heat event or an air quality advisory, trends like increasing temperatures or precipitation, or any kind of disturbances related to those and those changes in climate. And what we're most concerned about, of course, is to try to mitigate the impacts, the negative consequences of those things. We want to be able to prepare and respond for the negative implications of changes in climate. But of course, we also want to we want to make sure that we're taking advantage of opportunities as well. One pretty clear example of that is that, with increasing temperatures, we can probably expect our winter heating bills to go down as the temperature changes. But those might be offset by increases in utility bills in the summer as we have to start to add cooling. So just to try to be aware of those different trade-offs and make sure that we're pulling together a response, a design, and an operational strategy that can address both sides of that coin. When we think about resilient housing, there's some vagaries around definitions of what it is to be a resilient building. But when we think about resilient housing, we tend to think about buildings that are designed and managed so that they, of course, reduce the vulnerability to these climate-related risks. We want to reduce that exposure and reduce the sensitivity and improve people's capacity to adapt. We want to enhance people's personal safety, But we also want to promote social connectedness. And that really starts to touch on the idea that the stronger the connections that we have, the greater our social resilience, the more resilient we are to these kinds of impacts or stressors. So, the more people you know in your neighborhood, the greater your social network that you can draw on, the stronger the community within a building, the more resilient that community in the building will be. We want to do all this while, of course, maintaining affordability for residents. And then we also want to try to think about how these buildings can actually act as hubs for resilience outside just the building sort of envelope itself. How can they act as ways to maybe improve the condition or the resilience of the community more broadly? And there's some examples of how that might be done. You can create, kind of cooling shelters in these buildings. They can be created as networks, social network hubs. They can be green space areas that offer shade and respite in the summer months. There's lots of different ways to think about how it can extend out into the community. And there are lots of benefits to thinking about and implementing resilient design and operational strategies ahead of time. This is just some cost benefit estimates that were released for the community scale. So this is really thinking about on a municipal scale. But I put this here as a way of trying to illustrate that, for every dollar spent on improving resilience now, there are savings to be accrued in the future. And again, these numbers are based on community estimates. So we're talking about, streets and infrastructure and community preparedness overall. But it does apply to the building sector as well. When you think about, how I design my building now affects whether or not I have to do a major upheaval or renovation or retrofit in the future. So it's, there's ways of being thoughtful about how we design our buildings so that we avoid the need to do that kind of major retrofit later on, or at least reduce the cost of doing so. And then just another, just because this isn't enough to think about already, we also want to start to think about, okay, we already have the imperative to reduce our emissions. How do we start to couple that with improving thermal comfort and improving air quality? So these things can't be looked at in a vacuum either. Of course, there are lots of other imperatives that we're trying to achieve in the design of housing generally. And one of them that we concern ourselves with quite a bit at Integral is to improve energy efficiency and reduce emissions as well. And we start to think about that as low carbon resilience. So how can we find those design strategies that do both, that reduce energy efficiency or improve energy efficiency, reduce emissions, but also increase resilience and build, that social connectedness? How can we try to figure out ways of doing that all together? And there's lots of burgeoning research to indicate what those strategies might look like, and we're going to talk about a few of them in this webinar. A lot of the thinking that we have been doing along these lines really comes from the partnership that Integral and BC Housing have made, or in our support of BC Housing's goals within the confines of the Mobilizing Building Adaptation and Resilience project. This is a project that's been led by BC Housing, but that has multiple partners across the building sector and across the country. And the idea is really for it to be a multi-year, sort of multi-pronged project that seeks to identify what those strategies are that can achieve low carbon resilience, and then how can we start to build the capacity across the industry to understand how to best design housing that is low cost, resilient, low carbon, and livable and safe for their populations. So this is a project that we've been supporting for the last couple of years, a year and a half or so, that will be continuing on in the future. And there will be more opportunities to engage with it as we go through. But I want to finish by just highlighting a couple of the resources that we've pulled together so far out of this project that might be of use to those participating today. The first one is these resilient building primers that we developed. So if you go to the BC Housing website, you'll find a number of these, I think 6 or 8 primers that address different climate change hazards. So things like heat waves. We've also done some for flooding, for power outages, air quality events, and a few others that basically give a quick snapshot of, here are the design and operation strategies that you can implement, or that you can actually just sort of review in conversation with your design teams or with, with others involved in a project to see, are these things that we can start to do to improve our own building resilience? And I've highlighted here that it does talk a little bit about siting and design options for those new buildings that are being constructed or designed today. But there's also a section on how we can improve the resilience of building operations as well for all those buildings that are already in operation. And then I'll just end on this last slide, where we have also worked with them to develop a supplement to the BC Energy Step Code Design Guide. So hopefully some of you are already aware of the Step Code Design Guide. It was essentially created to help local governments and design teams, architects, owners understand what the strategies are that will help them achieve the highest levels of the BC Energy Step Code, so Step 3 or Step 4. But what we've done is released a secondary kind of supplement to that that says, okay, we want you to achieve those high levels of energy efficiency and reduce your carbon, but here are also the set of strategies that should be considered to help reduce your risk of overheating and of air quality issues as well. So this supplement is actually what a lot, I believe, of what Chris will be talking about in about 15 minutes or so. But just to highlight that these are available on the BC Housing website, and they're actually great resources to walk you through kind of the basics around how to improve building resilience to these two particular hazards. So with that, I will thank you for your attention and your participation. And I believe we're going to do questions at the end. So I will just be passing this over to Sadia, and she'll take you through some of the details on her work with BC Housing. Thank you.
Thank you, Lisa. Great presentation to understand that the climate change is real. My name is Sadia Afrin, Senior Manager Construction Services in BC Housing. A quick overview, this team provides the technical and functional leadership regarding BC Housing design guidelines, materials and methods, costing. We initiate also pilots in order to increase the efficiency and effectiveness in the social housing projects. As you know, the construction industry is fast changing. These teams also ensures that BC Housing design guidelines reflects that. And the next 15 minutes, I'll focus on BC Housing experience with overheating issues, one case studies, and our approaches moving forward. Let's have a few slides about our clients, partners, and affordable our housing portfolio. So as we all know that our housing clients are mainly low-income seniors, families, homelessness, individuals with disabilities, indigenous. It's a vast, diverse group that we serve. Our partners are mainly nonprofit societies, municipalities, developers, and so. Building forms varies widely from group home to townhouses to low to mid-rise wood frames to concrete high-rise. Lisa's presentation was very helpful, again, to understand that climate change is happening. Summers are becoming more hotter, becoming warmer, and many of you are familiar with the BC Step Code adaptation of the Step Code. The intention of the STEP code is mainly to reduce the reliance on mechanical and electrical systems generating heating and cooling and adopt the passive strategies, and a better building envelope to maximize the occupant comfort and minimize the energy use. So there is a great benefit of STEP code. Also, you need to understand the building will be much more tighter, and that will with the heavy insulation to retain the heat. However, uncontrolled solar heat gain through windows, our clients are becoming in the units, and Lisa already covered a couple of the key factors that is causing the inside temperature within the units is much, much higher. And it's increased over 21 degrees Celsius, exceeding ASHRAE 55 thermal comfort level, which is critical because you can see that when it's increased by 28 degree, it's already creating discomfort for our tenants. And by 35 degree, it's already a severe health risk. With that in mind, we had initiated a pilot energy modeling simulation in one BC Housing development project to understand the impact of overheating in residential units. The goal was to find out that how that building will maintain thermal comfort and indoor air quality with the current design and act to future climate. The pilot is an intersection. This pilot project is at the intersection of First and Clark Drive. The project is in response to Vancouver's affordable housing crisis, and also the urgent need of expansion of Vancouver Coastal Health's current Withdrawal Management Center that is currently at 377 East 2nd Avenue. The project includes 3 main components: 97 units affordable family housing, and a city-owned social enterprise space focusing on Indigenous healing and wellnessness to the employment, and Vancouver Coastal Health Withdrawal Management Center with 51 beds and 20 short-term transition beds, and also 2-level underground parking below. Vancouver Coastal Health patient will be on lower 2 levels. Housing residents will be vested in the top 2 towers. You can see from the left, and from the left tower is the Clark Tower, and to the right is the McLean Tower, 4-story, bisected by rooftop garden, actually the sky garden, in the 5th floor, and to further enhance the social connection between the residents. We had submitted the DP on May, and the construction will start August 2020. The project used actually the several passive strategies such as massing, orientation, landscape. You can see that operable windows that should meet the ASHRAE 55 thermal comfort requirements, and overheating 200 hours. That was actually part of our 2018 guidelines, City of Vancouver Energy Modeling version 2, and CWEC climate data, using CWEC climate data, which is the Canadian weather for energy calculation, historical data that BC uses for 2016. Energy targets are blended and based on the floor spaces, and we will meet the step code 3 for this building. Residential units consider in-suite heat recovery ventilations, and no cooling is provided at that time when we are starting the design, and amenities with the VRV system, heating and cooling. However, when considering the impact of the project for future climate data, as part of our EMBAR research, we found an interesting results. The energy modeling used future projected data, which is given by the PCIC, Pacific Climate Impact Consortium, for the year 2020, 2050, and 2080. Those are mainly the projection for the CWEC data 2016 weather file. And as you can see, as the climate gets warmer, the more months needs to be included in the overheating and comfort analysis. Currently, it's 5 months. You can see from the left, CWEC 2016, 5 months. 2050, it will be 7 months, and by 2080, it would be 9 months. The peak temperature is also increasing. You can see that it's increasing by 6 degrees, and on average from today to 2080, and the heating degree days will be decreased. Then we looked into the overheating mitigation strategies, and such as exterior blinds, solar heat gain coefficient, box shades, overhangs, and other operable window features. And you can see from the graph at the below, there are those bars in different colors for different passive strategies. And you can see by 2050, all these passive strategies is no longer adequately mitigate the overheating. And the graph is all over to the right. The graphs are all above 200 hours. Let's take an example of solar heat gain coefficient with 0.3, which is the gray bar to the left. You can see that it's currently below 50. That would not meet the overheating criteria by 2050, and the gray bar is actually exceeding 200 hours. Operable windows are typically having the most impact on reducing the overheating hours, but by 2050, even the operable windows cannot keep the overheating hours within 200 limit. So you can see the bar in different year and the color, and it's already increasing the 200 hours, and actually way above the 200 hours. Lastly, we looked into the room temperature and thermal comfort for tenants. This image shows the temperature distribution for level 6 suites on July 23rd at 5:30 p.m. So let me describe the graph, describe the image here. To the left, you can see the two boxes. One is actually the Clark Tower, and one is the McLean Tower, and there are different suites. by 2016, you can see that the graph, that the temperature is actually below 30 degrees. By 2020, the southwest corner is becoming hotter and getting above 30 degrees. By 2050 and 2080, to the left, to the below, below and to the left, 2050, and to the right, 2080, is becoming almost red in pretty much all areas. And that peak temperature is actually exceeding 30 degrees. When we take this data and put it into the impact with the operable windows, we see that by 2020, this peak temperature is actually getting above 32 degrees. And you can see that the blue solid lines is what is before is it's actually hard to do without the pointer, but I think you can see the below graph. The upper one, which is the dotted one, is the fixed glazing, which has higher, not impacted. But the operable windows for the residential units is the solid line. And you can see that the blue and the green one, blue and actually light blue one, is below 30 degrees, but the above one is actually increasing 32 and 36 degrees for each health, and that is already causing the health danger inside the units. From this finding, you can absolutely understand that the passive cooling strategies, such as utilizing the glazing with a good solar control and the operable window to increase the natural ventilation, will not be sufficient anymore, especially for the south and west facing. So a form of mechanical cooling should be considered in residential suites, which is recently not required for climate zone 4 and 5. For interior, though, for partly zone 5, 6, and 7A, it has full cooling and inside residential units in our current design guidelines. The most practical and the cost-effective way, while maintaining the affordability in the project in climate zone 4 and 5, is to have the partial cooling with the higher ventilation rates through the central ventilation system in residential units. Also, this will address the outdoor air quality that Lisa was talking about during the wildfires. The level of filtration for the central HRVs units by providing the MARV 13, and in addition, the space for future HEPA filter and also activated carbon filters. So the lessons learned, considering the microclimate conditions, overheating in residential is a serious problem, and it's really the effectiveness of the passive approach is good, but it may not be as effective as we have been thinking in the step code. So a form of active cooling, either partial or full cooling, shall be provided. To keep that in mind, in the BC Housing Design Guidelines 2019, we require all projects to meet the overheating threshold below 20. And you can see the highlighted red ones in the slide, that there are some changes that we bring forward in our design guidelines in 2019. So the overheating threshold should be not below 200 hours, but below 20 hours, because we consider our clients are critical. And that will be used if the CWAVE data 2016 has been used, meaning that if you're using the BC Building Code, not the projected data 2020, 2050, or 2080, then you must need to meet 20 overheating hours. Solar heat gain coefficient would be below 0.33 while maintaining the 60% visible transmittance. The reason we make it a balance, because when you make it go below 0.27, you can see that the highlighted in red. If you go below 27, we see that the visible transmittance level goes really low, and it's become very dark during the winter, and it's not very healthy for our tenants as well, being in the unit for almost 24/7. So looking at outside and operable lights would be helpful. And sufficient ventilation inside the units as per BCBC 9.32. Even though the building is part 9, part 3 buildings, we consider that inside the units they should provide the ventilation. The designer should provide the ventilation rates as per BCBC part 932. And we also ensure the mechanical we also encourage to provide the partial cooling through the central, semi-central or full or centralized ventilation system, as to bring not only the filter for the fire situation, but also to have the maintenance and building operation suitability. To ensure that all these things happening, we also added one compliance check, which is the BC Housing's third-party mechanical peer review before BP submission. So all BC Housing new development projects will require a third-party mechanical peer review to ensure that the mechanical design, which is pretty critical to bringing and reducing and addressing the overheating challenges recently. Lastly, I would like to show you one document that we have recently created. This is the BC Building Code, the challenges that we addressed from the BC 2018's requirement for fire and smoke dampers at various locations in residential buildings and ventilation systems that would impact affordability and central ventilation system. So meaning that when you, currently BC Building Code, I think many of you may know that it's required the fire and smoke dampers requirement, and providing that fire and smoke damper requirements for ventilation, a central ventilation system would significantly increase the cost of BC Housing projects. So we recently came up with a performance-based solution for BC Housing mid-rise projects, and this applies only for BC Housing projects, knowing that we take other mitigations and other solutions, other alternates for this solution. The guidelines will overcome the barrier and providing the cooling in residential units, and City of Vancouver has already adopted this alternate solution already. So with that, I will end my presentation and pass it over to Chris.
Okay, thanks, Sadia. So I'm going to spend the next 20-25 minutes sort of going into the next layer of detail on specifically on passive and active systems that have both Sadia and Lisa have touched on in their presentations. A quick overview. Basically, how overheating and the strategies to mitigate it can impact step code targets. We'll touch on that very briefly at the beginning, and then we'll go into specific detail on the passive systems, how they can be incorporated, and then segue into the active systems. And as Lisa's touched on already, a lot of the work that we've done here at Integral in supporting BC Housing and with BC Housing is captured in the design guide supplement, and a lot of the work that is presented in my presentation is taken from this document. So we all know that overheating is something we want to mitigate, and we need to work at and find the right solution to do that. But we have to balance that with obviously meeting the step code targets. And there's a lot of variables that are at play, a lot of things to consider, and it's really important to do a good level of analysis fairly early on in a project, and do that, create a matrix of options and go through the opportunities and challenges with each, and make sure that you have the tools available to you to produce the information you need in order to get a clear understanding of what could work for your building and the context that it's in. For example, here we have a very simple room. We find that exterior shading certainly reduces the risk of overheating significantly, but that will also increase the thermal energy demand intensity. So that means we're not allowing the sun to come in during the winter times, and therefore we're requiring more of a mechanical heating system to compensate. we'll talk about operable windows in some detail later on in the presentation. Again, a good way of reducing overheating, but there's challenges with poor indoor air quality. So mitigating the risks and finding that sweet spot is key. Lower solar heat gain glazing, another great way to reduce overheating. Again, it increases the thermal energy demand intensity, and it's through modeling and analysis. You can find the sweet spot where it's cost effective to use a method, not only to reduce the overheating, but also to make sure we meet our step code energy targets. And then finally, if we have to include mechanical cooling, then understanding its impact on the total energy use intensity. So that's the total use, the total energy use within the building. Obviously, using electricity and mechanical means to cool a space will incur an energy penalty, but again, it's mitigating the risk of overheating and providing the resilience to the building and finding that balance point. So we'll now dive a bit deeper into passive systems, and where we want to start is with passive, and this is essentially passive systems are systems where we're trying not to use electricity or any mechanical means to provide thermal comfort to a space or to a building. We want to leverage the architecture and the structure where we can. We've already had to invest in those, and we want to get maximum value. They can have some of these elements can have significant impact and help us mitigate overheating very effectively. In the top left, you have the what we call thermal mass, and this refers to the material's ability to absorb heat. So things like concrete are a very good absorber of heat. It can absorb heat during the day, and then we can release that heat overnight when the outdoor temperatures are typically much cooler. And just by opening a window or flushing a small amount of air through a building, we can dissipate that heat overnight. The concrete structure of the building is then ready to store all the heat for the next day, and this allows us to cut the peak of the curve that happens in those internal space temperatures. So it would significantly reduce that. The next key element is the amount of glazing. So obviously, sunlight is entering a building can be a significant contributor to overheating. It adds a significant thermal load to a building, can be equal if not greater than the internal gains within a building. And so understanding the glazing areas and designing appropriate glazing areas is key to mitigate the overheating. But also we want to make sure that we're not penalizing ourselves by shutting out useful solar gain in the winter time. So finding which elevation is the best elevation of a building, depending on its orientation, its site characteristics, the neighboring buildings, all of these things need to factor in to find, again, that sweet spot of allowing a decent amount of daylight in to create a great space to be in, but also mitigating the solar gain element. And so once you've moved on from glazing, obviously the shading component is very key. Trying to maximize glazing where it's of benefit to us at certain times of the year means we probably need to focus on a good shading strategy for the summer times. And there's various different ways to do shading. Perforated screens, we can have horizontal on the southern elevation that's really effective. Looking at vertical shading on the east and the west can be very beneficial for those lower angle that lower angle sun. But trying to find again that sweet spot of being able to utilize the solar gain when we want it is something to consider. Thinking about manual or active shading, such as the blinds at Olympic Village, very effective of being able to control when the solar gain is brought into a space. But these obviously do have a maintenance and perhaps a cost burden. So all of these things need to be factored into any design decision. There's also the opportunity of using planting or trees. These are very effective at shading the sun in the summertime, and then particularly deciduous trees, if in the wintertime, can allow that useful solar gain to come in during the winter. So considering landscaping around buildings, how many floors could be shaded using this kind of strategy is good to think about. And creating a matrix of going through all the different types of shading, this is actually within the design supplement, and tries to give an idea of where the focus should be, or what would work best for your project. Each shading device has benefits and has some challenges as well. So again, making sure you're analyzing all of the options available and making sure you've got the appropriate solution that will have the maximum impact and be very effective in mitigating solar gain through the use of shading. So now we're going to move on to the next stage. Once you've leveraged the architecture and the structure of the building and created a shading strategy, is how can we create cooling through passive means? And one of those ways is through natural ventilation. And by natural ventilation, we mean creating an opening in the facade that allows good amounts of outdoor air to flow into a building. This can be used to cool a space, remove the heat, and also the actual feeling of movement of air can give occupants a feeling of cooling, which can help with them improving their thermal comfort without the actual air temperature being significantly reduced. And so here we got some images showing different ways of doing it. The top left is a single-sided approach where you just would create a single opening on one side, and that can be effective to bring air in, but you have the air coming in and going out on the same side. So it's limited in its effectiveness, and the depth of the room will have a really big impact as to how effective this can be. If we move over to the top right, this is a cross ventilation approach where you have openings on two sides. This creates a really good amount of airflow across a building. Even on a still day, when there's no air movement, you'll have a difference in pressure between sides of buildings, and air will transfer from the positive side to the negative side. And that actually is a very natural way to promote good airflow without the use of any fan or electricity. And it's the volume of air and the rate of change in a natural ventilation strategy that has the maximum impact when it comes to delivering good thermal comfort. And then in the bottom left, just finally, we'll just on this one, you leveraging openings at two different heights allows you to create a sort of very small stack effect, and the stack effect is again leveraging the height. Warm air is more buoyant, and so it will rise. And so creating an opening where warm air can rise out of a space, it will be replaced by other air, typically cooler air from outside. And so this is a very important and effective strategy to deliver thermal comfort very effectively. But one thing that's key to making sure this strategy has its maximum impact is understanding what we mean by an opening. The actual when we size openings, or we size these natural ventilation openings or windows, is making sure we're talking about the same thing. And when we talk about it, we're talking about the actual area that is open to the outside, not just the physical area of the window, but actually how much does it open? What is the area that's exposed to the air that is outside? And as you can see on the image on the left, that's a combination of the side triangles. This is a top hung window. You have two side triangles, and then you have the openable area at the bottom, and you'd add all those together, and you'd get an effective area, and that can be used in some engineering calculations to understand how much airflow would come in, and that in turn can then dictate the effectiveness of the solution. When we talk about depth of travel of a window, understanding what is the context of the window detail, how deep is the external sill, how deep is the frame. You can see in the image on the right that the length of travel from the window frame to where the edge of the window is when open is quite significant. But because of the deep external sill, the actual effective opening is very minimal, and this has a dramatic impact, a negative impact on the amount of air that would be able to come in. Again, we're not using fans, so we have limited pressure to push air or to move air into the building. And so making sure we have limited, minimal resistance is the key to a good natural ventilation solution. Just to give you some sort of examples of things that have worked and things where they've become challenges, you'll see on the left, this was a sketch of the intent for a design where there is restriction typically for windows that are below railing height, and all windows usually in residential buildings, that they're restricted to 100 millimeters, and that's for safety reasons. But understanding where that 100 millimeters is applied is key to making sure we get maximum effect of the investment of creating a hinged window. And you'll see on the image on the left that the 100 mil was taken as from the window frame, which is the vertical piece, to the inside edge of the window. And that was the opening that was designed, and that was what was expected. And then the image in the middle is actually what was ended up on site, where you could see it actually, the 100 mil was actually taken from the further in the frame, and so therefore the effective opening was significantly impeded due to the thickness of the window frame and the window itself. And then on the right hand side is a solution on a project I've done previously, where we actually created openings where they hinged internally, but created an architectural screen on the outside. And this was a really effective way of allowing maximum airflow for any opening that we created, while still maintaining the security and the benefit. It does require using a window product to give you that good hinge and to give you that good that thermal break and that tight air seal that you want to make sure that your U value and your thermal envelope performance is highly effective. But it's a really effective way of getting good airflow with a very simple hinged opening. One of the challenges that stops people from looking at natural ventilation as an appropriate strategy is noise, and a lot of sites, such as the Clark and First site, have perhaps some noise concerns. Again, key to occupant comfort, not only thermal or indoor air quality, but acoustic comfort as well. And so there are options out there to create attenuated openings. These are openings where you have they allow air to come in, they're designed to have minimal resistance, but they have some form of acoustic absorption that absorbs all the sound from outside, and you can get significant reduction in the sound level from outside to inside just by using these strategies. And there's a key part to this is applying the sort of engineering rigor, essentially. It is important to make sure that things are fully designed to be effective. And there's a number of ventilation standards out there. Certainly the ASHRAE 55 that's been adopted by the City of Vancouver Energy Modelling Guideline is key, and that was referenced again as well by Sadia. In terms of temperatures cannot exceed 80% of acceptability limits for more than 200 hours during summer months, or 20 hours for more vulnerable populations. So this does set a engineering challenge or a design target, and so it's important to make sure you can deliver and meet those. An alternative we found a lot of impact and success with is the Chartered Institute of Building Services Engineers guidelines. These are design methodologies for both non-residential and residential buildings. And specifically the one with the residential buildings is actually focused on maintaining good thermal comfort within bedrooms. Sleep is key to to people's health and well-being, and it's difficult to sleep in a very warm bedroom. So that sets the limits of what maximum temperature should be achieved, and for how many, what percentage of the nighttime hours, and also sets an absolute maximum daily temperature for each room. But through the use of energy modeling or thermal comfort modeling, we can model any space to demonstrate whether they meet these guidelines or not. And we can look at future climates, whether it be 2050 or 2080, and factor all of these things in, again, to demonstrate that what is the appropriate solution in order to deliver good thermal comfort. So taking the slight next step and just introducing a small fan or a simple exhaust system, or even a ceiling fan, can give some real good benefit and improve the window of opportunity for natural ventilation to be applied. A ceiling fan, especially in the bottom image here, has a real big impact in promoting good thermal comfort with very simple natural ventilation, and extending that window of opportunity that can be used in the year. So something to consider through the design process. But we know that passive systems alone aren't likely to meet the thermal comfort requirements of buildings as we move through to 2050 or even 2080 climates. And so we have to consider the use of active systems. And basically, an active system is using typically fans, and it may include some form of cooling to change air temperatures, and uses electricity. So again, understanding what level of active system is appropriate for a building in order to mitigate the risk of overheating, but also to make sure we're not using energy where it's less effective. And so a good starting point for any active system is looking at what equipment you already have in your building and trying to leverage that as much as you can. So can we leverage the heat recovery ventilators that are typically provided in all buildings? Heat recovery is very effective and very good in the winter, reducing the thermal energy demand intensity of a building, and ultimately the total energy use intensity. But that heat recovery is something we don't really want in the summer times. So can we look at making sure we're using units that have 100% bypass? So the image on the left here is the HRV, a heat recovery ventilator, in full heat recovery mode. Heat is transferred from the return air to the exhaust, to the supply air, to the outdoor air as it enters into the building. And then on the right, we have, it's in the same unit, but in full bypass mode. And the outdoor air comes in, it actually bypasses around the heat recovery and goes straight to the indoor space. And the outdoor temperature, typically in shoulder seasons, is very effective at mitigating overheating and delivering good thermal comfort. And it's important to make sure we've got 100% bypass. It's very easy to create this opportunity in more centralized ventilation systems, but on a suite by suite system, it may be more challenging. So again, a consideration of the equipment. Also, the abilities to actually increase the airflow, the outdoor airflow, can be very effective. We're using fans, so it's technically an active system, but the ability to have increasing the capacity to bring in more of that cooler outdoor air when it's useful is something to consider. So it may mean increasing the capacity of the unit slightly, and increasing the size of ductwork, but understanding the impact that can have on mitigating overheating, and comparing that against the capital cost investment is one way to is leveraging what equipment we have, and can be very cost effective. But ultimately, we may get to the point where we need to add in mechanical cooling. There's many ways to do mechanical cooling. You're essentially looking to just effectively remove heat from a building. It can be done either through providing cooling units within each space, or it could be done through the ventilation system. Which method is appropriate is dependent on sort of the size and building and the ultimate design decisions that are made, but both can be effective. But understanding the impact that mechanical cooling can have on things like step code energy targets, we want to make sure we're leveraging technologies and equipment that has a low carbon emission. Is a low carbon emission source, and is very effective and very efficient. So things like heat pump technology, where you can actually take one unit of energy can actually give you 3 to 4 units of cooling, is a very effective way to deliver cooling to a building while still maintaining your energy efficiency as much as possible. And then there's sometimes a financial challenge on projects. Current climate may or may not, depending on the building design, may or may not require mechanical cooling. So understanding how could cooling be integrated in the building later on is something that should be looked at if there is a capital cost challenge during the design process. Do units need to be have the appropriate space in them? Do you need to introduce piping into the building at a later stage? Do you create the pathways to do it now? All of these things can be considered in order to, again, provide a degree of resilience within the capital cost budget that's being used on the project. How you distribute cooling can actually have a big impact on the capital cost. Again, if it's centralized, it can be fairly cost effective. You're providing cooling from a single unit. The level of control needs to be considered. Different elevations will experience different degrees of thermal comfort or overheating potentially, primarily based on the position of the sun. So understanding control on a central system and how it can be implicated in a cost-effective manner is something to think about. And then you have moving away from a central model to a distributed, where you provide cooling more on the space-by-space level. The middle image here is the floor-by-floor, where you have a very simple heat pump, and that's providing cooling on a per floor. Can be very cost effective, but does take up space on the floor plate potentially. Something to be considered. How do you maintain the equipment if it's all distributed through the building? Things like these things need to be factored in. And then you've got the specific space by space, where each individual user or occupant would have control or ability to change their space accordingly. Typically, the more control you provide and the more flexibility, the capital cost increases and the complexity. But again, it's understanding what is the risk of overheating and what is the most appropriate way to mitigate it will be dependent on many of the project context. One way, though, to deliver really good resilience to a building to mitigate overheating is to actually look at leveraging both passive and active means, and the leveraging of natural ventilation in combination with some mechanical cooling is a really good resilient approach. So here we have sort of 3 different scenarios through a year. This building has both openable windows, and it has a heat pump and a HRV unit, essentially just basic mechanical systems. So during the winter, the windows are closed, you have the heat pump providing the heat, and it's distributed through the ventilation system, and that's keeping the occupants thermally comfortable during the winter. Then as we move to the shoulder seasons, you can actually just switch off the heating mode, and you can just be potentially bringing in direct outdoor air through the HRV. You've gone into bypass mode, and you're bringing in 18 degrees C air. That's going to keep occupants really comfortable. And you also have the ability to open windows to dramatically increase that airflow. Typically, mechanical systems are designed to achieve 1 to 2 air changes an hour in a space. That is, the volume of air in a space is changed out once every hour. And when we use natural ventilation, we actually look to increase that to 4 to 6 air changes an hour. And that dramatic increase in air volume is what allows people to feel cooler and comfortable. And then when you move to perhaps during the peak summer, when natural ventilation alone will not do it, it's 32 degrees outside in this example, you actually close the windows, you isolate the space from the outdoor condition, and then you just leverage the mechanical system again through delivering cooling through the ventilation system to provide occupants with that thermal comfort that is needed and warranted in these conditions. So that's that on ventilation. That's a sort of a segue here into sort of air quality that is associated with all of the ventilation systems. Obviously, air quality is important. There are many sources of poor air quality. And they can be both internal and external. Things like cooking. Or off-gassing of cleaning products and materials. So good ventilation is always warranted and desired for those. But also a number of external outdoor air pollutants. And so understanding what the local environment is around the proposed site is good to understand. There is some guidance in terms of what should be expected. That's in BC Building Code. But for those that are looking for the next level of detail and a more defined standard, the LEED and WELL standards are very good at defining what is good indoor and outdoor air quality. So, and understanding the context will impact the design strategies on how to make sure we're achieving good indoor air quality. And some of those strategies are primarily focused around the ventilation system. And so when we're using a mechanical ventilation system, the level of filtration is key and is a fundamental way to deliver good indoor air quality to a building and mitigate the external pollution. MERV 13 filters is the minimum requirement captured under LEED. These should probably be the minimum on projects, and if possible, even consider going to much higher, like MERV 16, things like that. Understanding the local context, as I said, may require the need for carbon filters if it's a highly air polluted site. Then understanding what that means for a system and how they can be incorporated into a unit may impact the ventilation solution. It's more cost effective to do high performance filtration in a centralized ventilation system than it is in a distributed ventilation system. So all of these things will feed into the design process. Forest fires, we know, are increasing and are going to become more and more of a challenge. So understanding how can we mitigate that? It's only for a short period of the year. One of the benefits of air handling units and heat recovery ventilators that they're designed to operate with a dirty filter, which means they have a bit more capacity when you put a clean filter in. And so there's an opportunity to take out the more typical MERV 13 filter and perhaps put in an additional filter or even a secondary filter that could provide a higher degree of filtration without dramatically impacting the output of the unit and the ventilation flow rates to the building. And then understanding where your air intakes are going to be is key, making sure they're located away from any pollution sources. And finally, so that's quite a lot of information to go through, quite a lot of different systems, a lot of decisions to be made, and there may be some capital cost implications. But understanding that you may not have to do it throughout the whole building. You may not, it may not be feasible to deliver good thermal, to deliver mechanical cooling, for instance, throughout the whole building. So is there an opportunity to create a refuge, a space within a building that occupants could go to when their own personal space perhaps isn't able to maintain the thermal comfort that is warranted or desired? So creating a space within a building, a community space that could have things like additional mechanical cooling with higher levels of filtration. Could they have backup power to further improve or increase the level of resiliency in a building? Is something that should really be considered to allow both occupants and even the local community to have resilient buildings that they can live in and work in as needed. Okay, that's all I've got. I think I'm passing back to Jackie now.
Great. Thank you so much, Chris, for all the design strategies. Thanks, Sadia, for a great example of BC Housing's design guidelines, and Lisa for laying the context. We have a few questions from the chat box. Edwin Guerra has a question for Sadia. So beyond the somewhat arbitrary 200-hour limit, do you have an indication of how many more hours are actually exceeded, and by how much in 2050 for the project?
Thank you, Jackie. We actually, the simulation, I can bring the slides if I can. I need to show the graph. Okay, so you can see from the graph, actually, mainly these slides, you can see that when we did the biggest challenge for this simulation was that we cannot take everything into one calculation. So when we did the modeling report, we couldn't do all the factors at once. So what we did is like one factor and the impact at a time. So that we get the results. For an example, in this slide, you can see previously it was by current CWEC 2016, if the effectiveness of that is 28% for reducing the overheating by providing the operable window, or kind of the other passive strategies, it's not very effective anymore by 2050. So it's only 30% effective to reducing the overheating by 2050. So you can see that it's between 200 to 250 hours. But again, be mindful that this is not a combined factor. This simulation is only done one factor at a time. So this one was done kind of not in the combined. So for an example, tenant being inside the unit for 24/7, their appliances, lighting, and all these has not been impacted in this, has not been accounted for this data. So even though it shows within between, it would be way more than what we expect by 2050.
Okay, thank you. Thanks for that question, Edwin. Kim Gallagher has a question. I believe it's pertaining to step code requirements when they became mandatory. So the question is this concept for new buildings being built now, or has it been put in place for recent buildings that have been built? We have built a building that opened last August 2019. Would this have the cooling to try to prevent overheating? I guess anyone could answer that one. Chris or Lisa?
I'm wondering whether Lisa might be better.
Okay. So,
sorry, can you clarify the question? So is the standards that we've been presenting today, are they applicable to new buildings only, or are they standards that have been applied more broadly? Sorry, can you just clarify for me?
Yeah, it's whether these standards would have been implemented for buildings in August 2019.
Oh, I see. Right. So the design guide, I mean, I'll interpret it the way I think I understand the question. So no, in terms of the strategies that are presented in the design guide supplement, this is meant to be guidance only. So there are many roads to designing a building that would meet the requirements of the BC Energy Step Code. And these, the strategies are in the original design guide are really just, similar to what Chris has provided, are sort of rules of thumb that generally tend to apply in many cases, but that still require a building by building approach to understand what the strategies are that are best going to apply to that particular building in that context. So they're by no means, do all of these strategies all of the time. And they're not requirements either. They're just suggestions for means of, methods for achieving the energy efficiency targets under the BC Energy Step Code. Likewise, those that are presented in the supplement are strategies that should be considered, but that need to be adapted for, the building in question. When it comes to the City of Vancouver's energy modeling guidelines, those have been issued, around the requirements and the limits around overheating. Those are required part and parcel with the application of the BC Energy Step Code, so they would have had to be followed in the rollout of the step code from its initiation. But there's already a version 2, and those are likely going to increase, or they'll be continuously revised. And I know that the City of Vancouver and the province are both actively looking at how those should be adapted to account for a future climate, including potentially a requirement for modeling using future climate and weather files. So hopefully that answers the question. If not, please clarify in the chat window and I'll try to answer it better.
Lisa. Another question from Edwin pertaining to the actual CWEC files, the Canadian Weather Year for Energy Calculation files. I think this might be for Chris. Do you know what the diurnal or the daily temperature range in the 2050 CWEC files, and are they freely available for projects?
That is a good question.
I can tap that, Chris, if you want.
You go first. Yeah.
Yeah, okay. So actually you can get that access because PCIC actually put it into their website now to retain those. Either that will be applicable to the project or not, maybe that's the discretion to the design team. But we did in the First and Clark project, as an example, we did actually the future data for 2020. We did not use the CWEC 2016 data for the building peak design calculation. So I think there is a consent from the design team whether they would be using those data, but we highly recommend that that to be used at least 2020 and 2050 data, and that are available in PCIC website now.
Great, thank you. And to Lisa, yes, Kim says that answered her question, so thank you both. Don't see any other questions in the chat box. Are there any questions or comments from Lisa, Sadia, or Chris?
I actually have a question for Chris. Sorry, Chris. When you showed the graph of how to manage from winter to shoulder seasons to summer, I mean, it obviously requires a building operator that is kind of monitoring what season you're at and how the units might respond, and at what point those strategies should be put in place. So are there any, I don't really know my question, that's sort of like a consideration, I think, that there needs to be that very careful handover from the engineers to the operators to say, this is how it will best operate. Are there any, do you know of any kind of strategies or resources that can be used to, make sure that information is passed to operators so that the building is managed to the best of its capacity?
Yeah, I mean, I think there's certainly establishing a clear basis of design right up front with the client and the designers, so everyone is on the same page. Everyone understands the level of control that will be provided and what that means. As we move then through sort of the end of the construction process into occupancy, doing that handover, both from a commissioning perspective, making sure you have the right level of commissioning that's on the project, and also actually providing a guideline for even building occupants, understanding how they should be using their space, what they should be considering at different times of the year. If this is happening, then perhaps then doing X. If this, then do Y. And so they can have a degree of autonomy as well. Again, if they're given the right guidelines. And then there's actually ways to keep design teams engaged through the first year, if not beyond the operation of a building, to understand and extend that period of time that designers have to transfer the knowledge and go through the full year's climate, essentially, and refine systems as needed to make sure that they are delivering A, as intended, and B, creating the thermal comfort for the occupants.
That's a really great point, and something that pertains to commissioning, which we were talking about prior to this webinar. Related to that, Kira Peterson has a comment that said, we've seen airtight passive house projects recently completed that they needed to go back in and add mechanical cooling following the first summer season. And that I would expect that most projects that don't have some form of passive or mechanical cooling measures, as you mentioned, will need to investigate options to reduce overheating in the coming years, and much sooner than people generally think. So that is definitely on trend with what I've been hearing here today. Yeah, and also, I guess I could segue into the next. Those are, speaking of existing buildings, we will have some webinars that are talking about how to address after the building is built, overheating. So I'll make mention of that at the conclusion here. Let me just check this chat box for any votes. Yes, so Lena's son said, we have buildings more than 40 years old. Is it possible still to implement a new way of systems to reduce the heat? And certainly we will get into that next time. So if there's I don't see any other questions here in the chat box.
Can I ask just a quick one?
Yeah, please.
Of Sadia, actually. I'm curious, that, having gone through MBAR and, arguably one of the most extensive processes for future climate modeling on a building so far, are there any kind of pitfalls or lessons learned, like things to avoid, that you would impart to others in doing the same? Like, oh, we tried this and it was a nightmare, or, definitely do this or something like that. Are there anything, just sound bites that you might share? I'm very curious.
Thanks, Lisa. Yes, definitely one challenge that we had is by implementing the central ventilation system or semi-central system, because currently, that's my last slide talking about the alteration that we put as a document for alteration to BC's 2018 requirements for fire and smoke dampers. So what happened is that, because when you have the central ventilation system, your vent and ducts goes into the individual units, and those individual units, and even below, like even within the 5 inches or 6 inches ducts, you need to provide the fire and smoke dampers that needs to be connected with the fire alarm system. So you can imagine in our building, like say First and Clark is an example, 97 residential units, you have to have 97 smoke and fire dampers connected with your fire alarm system. So it was a huge pushback from our design team, and what happened is, like, they were not putting any sort of cooling especially for zone 5 and zones 4, which is not required anyway until the historical data, if they use the CWEC 2016. But we had a difficult time, and through the peer review process, mechanical peer review, I talked about that all BC Housing new construction project will go for third-party peer review. When we did the compliance review, we found that it's really almost like a challenge for the design team as well, and affordability for social housing projects. Because every connection, every smoke dampers, it will need about $1,500 to $2,000. You can imagine 97 units, they're entirely not putting any semi-central or central systems. So we came up with a document. The document is created by SNES Consulting, a code consultant, and kind of a consultation with the mechanical consultant from the industry, and also the code consultant from the industry, as well as building safety branch. And also City of Vancouver was actively part of that. And so we cannot put it as a technical bulletin. The reason is because authorities having jurisdiction still needs to have their sign off on that, right? They need to approve that. So City of Vancouver came up and they accepted that alternate solution, which is excellent. Some of other municipalities such as Hope, and Hope actually did for one project. And we are closely monitoring City of Surrey, City of Burnaby, other bigger municipalities, how they're coming. So we're monitoring those through the building permit process. So this is one of the big challenge to implement the central ventilation system in social housing projects.
Fantastic. So I'd like to thank our presenters, Lisa, Sadia, and Chris, for sharing their expertise this morning. Thanks so much. And thank you to our partners at BC Housing and to the City of Vancouver to help bring these webinars to you. Our next webinar will be on May 13th. It's addressing overheating in buildings for operational staff, where our presenters will also be addressing the issue of overheating amid the COVID-19 pandemic. And the following webinar after that will take place on May 26th, pertaining to retrofits to respond to extreme overheating in buildings, and as well as poor indoor air quality. So we hope to see you there. That concludes our webinar, and we hope you have a great rest of the day.
Great, thanks very much.